This is going to be a very brief video on summation notation and series. Summation notation looks like this. I is called the index of summation. The 1 in this case would be called the lower limit of summation. The n in this case would be the upper limit of the summation. The a sub I would refer to the sequence that we are going to add together. This particular summation could be considered the first n terms of the sequence. Since sum means add, we're literally going to add all the terms of the sequence together. Here in this particular example, we're going to need to find out what a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5 are. You can see that we're starting at 1 and we're stopping at 5 based on the beginning and ending points there. A sub 1 would be 1 factorial over 2, or 1 over 2. A sub 2 would be 2 factorial over 2, or 2 over 2. A sub 3 would be 3 factorial. 3 factorial would be 3 times 2 times 1, or 6 over 2. 4 factorial would be 4 times 3 times 2 times 1, or 24 over 2. And then 5 factorial would be 5 times 4 times 3 times 2 times 1, or 120 all over 2. Now, I'm debating about whether we want to reduce our fractions or leave them. The nice thing about leaving them is we conveniently have a common denominator with all of our terms, so we should be able to add them together relatively easily with our common denominator and get a 153 half. I'd like to quickly go through a couple properties of sums. In this particular case, we want to look at what if we took the sum of a constant number. Well, a constant number isn't changing, so if I started a sequence where all the numbers were the same, wouldn't I just take that constant number times the number of terms in the sequence? You can work yourself through an example like that by doing something along the lines of this, from 1 to 4 of 5. Well, this would be literally 5 plus 5 plus 5 plus 5, or 4 times 5. Likewise, and this second property is something that could have been helpful perhaps in our last example. If I have a constant being multiplied within a sequence, I can pull that constant out and do the sum of the sequence, that the part of the sequence that's changing, and then do the rest all times that constant. If we take a look at our last example, we could have actually pulled out this half and made this the sum going from 1 to 5 of simply an I factorial. Meaning we wouldn't have had to add everything together as a fraction. We could have added all the pieces, multiplied it by a half. We would have still ended up with our 153 halves. These last two properties are virtually the same. If I'm able to take two separate sequences, and sometimes they're not listed as two separate sequences, but you can see that they're kind of acting independently, we could write this as the sum of the first sequence and add to that the sum of the second sequence. Let's write out this example real quick. We'll leave it in variable form here. I'll maybe pause and write so that you don't have to watch me write this. If we were to put all these terms together, you'd see we'd take the first term, we'd add it to the second term and the third term, we'd go all the way to the nth term. Well, you'll notice everything here, if we took away the parentheses, everything is a subtraction, or I'm sorry, an addition. So we could rearrange. The commutative property of addition applies greatly here. And if I move all of my pieces so that the A pieces are all together, that's going to become a summation of all the A pieces. And I move together all the B pieces, you'll notice all the B pieces get added together, and that's how we can kind of separate this property of this summation into two separate summations. Like if we were to do this with a subtraction, I think you can see the same thing would occur if for no other reason, let's just write it out real quick here. We can take and subtract two separate pieces. If for no other reason, I could argue that this was simply an a sub I plus a -1 times a b sub I right here. And if that's the case, then I can separate it based on the last property on the addition. And with the constant multiplier, I can pull that factor out, and that together is going to get us that subtraction there. All of these really are series. A series is simply the sum of the terms of a finite or infinite sequence. Finite sequence would simply be something that started at 1 and went to some particular value. I threw a k in there because I wanted to try and change it up a little bit. An infinite series, and yes, you can add up an infinite number of terms, would just keep going to infinity. Not all will work, but some will. We'll look more into that later.